This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
Good morning. My name is Mike Huron, and welcome to the latest in CAE Associates e-learning series. Today we'll be talking about fluid force and drag prediction using ANSYS CFD. Now, a quick administrative note before we get started. We will be offering 1 PE credit for those of you who are interested. We just require that you participate in our polls and also our follow-up survey afterwards. So as long as you do that, we'll follow up with you on the PE credits. Okay, so what's on the agenda for today? Well, first we're going to talk about predicting fluid forces, what that means and why we're here talking about it today. And then we're going to move on to meshing and modeling for force and drag prediction. So what are some things that we need to, in particular, be on the lookout for in order to, when we're creating models to predict force and drag. And finally, post-processing and interpreting results using ANSYS CFD post for these types of analyses. Okay, so from common experience, we know that as an object moves through a fluid, it will encounter resistance from the surrounding medium. Obviously, everybody's experienced that. And predicting the resulting forces is important for many engineering applications. And some of these include lift and drag acting on airfoils, around automobiles, or the hull of a ship. Instances like torque in rotating machinery, or forces resulting from internal flows. So certainly these come up a lot in engineering applications, and we're going to want a tool to accurately predict forces in order to characterize our devices. Now, the example that we're going to use today is a typical external flow, flow past an automobile. And a common quantity of engineering interest is the coefficient of drag. So the drag force normalized by 1/2 times the density times the free speed velocity times the squared times the cross-sectional area. Now, prediction of the coefficient of drag relies on the prediction of the drag force. And since the drag force acts on the walls, we're going to need to pay close attention to the flow in these regions. So it's going to require accurate near-wall results. Obviously, anywhere that we're going to want, we're going to use for our evaluating our device, we're going to want to make sure the results are accurate in that region. So if we need accurate near-wall results, what are some things we should consider when we're generating our mesh? Well, if we think about the drag force, we can basically break it down into 2 components, the form drag and the skin friction drag. Now, the form drag results from the shape of the body itself, and so in order to accurately capture the form drag, we're going to want to make sure we have sufficient mesh resolution so that we capture the surface pressure variation. So you can see in our example here, we have a relatively, a moderately fine mesh, and when we go in post-process, we're going to make sure that our pressure contours are both physical and smooth. Now, the skin friction, on the other hand, is a result of the shear stresses at the surface. And in order to accurately capture those forces, we're going to want to make sure that we are able to capture the behavior of the boundary layer. And in order to do so, we want to generate inflation layers at the solid boundaries. So you can see in our mesh here, we have inflation layers around all the solid boundaries of the sedan body. Now, when we're generating that mesh, we need to take into consideration what our modeling approach is going to be. And one of the first questions that we need to ask ourselves is if we want to accurately capture the flow near the wall, we must first understand what the nature of the flow is. Is it laminar or is it turbulent? The flow itself can be characterized using the Reynolds number, which is a measure of the inertial forces to the viscous forces. And if it's sufficiently high, the flow will be turbulent. So some examples of a critical Reynolds number where the flow will become turbulent are for flow along a surface, a Reynolds number of roughly 5 times 10 to the 5th. For an internal flow, a Reynolds number of a much lower threshold of around 2,300. Now, for most engineering applications, we're going to find that the flow is going to be turbulent. And one of the implications of turbulent flow is that the gradients near the wall are going to be very steep. Now, typically we have 2 different approaches for dealing with resolving the near wall flow. First is the near wall resolving approach, where we have a mesh that's fine enough to resolve the turbulent boundary layer all the way down to the wall. Now, this can be very costly, especially very close to the wall, where we're going to need very fine mesh spacing, and can often be prohibitive or difficult to implement for complicated geometries. Now, fortunately, the profile of the near wall conditions are often predictable, and what we found through experiment and mathematical analysis is that the velocity profile near the wall, the non-dimensional velocity profile near the wall, is quite predictable. So as an alternative to the near wall resolving approach, we can use the logarithmic-based wall function approach. And you can see in the bottom right the difference between the 2 mesh requirements in our pictorial here. So using the predictability of the near wall velocity profile, we can use the wall function approach to bridge the gap from the outer fully turbulent region to the region very near to the wall, where our mesh requirements are going to be steepest. So from that outer turbulent layer to the inner viscous sublayer, we're going to use the predicted wall profile instead of fully resolving that using the mesh. And so this provides for a much more economical approach to predicting the near wall profile, but it is based on the assumption that the boundary layer adheres to this predicted profile. So in order to use this, we're going to make sure that our first node is in the log region, so roughly a y plus of anywhere from 30 to 150, to make sure that the wall function approach is being implemented correctly. Now, in some flows, the log-based wall function approach is not going to correctly predict the boundary layer profile. An instance of this is if we have boundary layer separation. For instance, in our pictorial here, where we have reverse flow, obviously in this case, the boundary layer profile is not going to adhere to the predicted profile that we showed on the previous slide. Now, if this is a dominant feature of your flow, then the log-based wall functions should not be used. Alternatively, we're going to want to use the near wall resolving approach or the automatic wall functions in CFX, which can provide more accurate results. Okay, at this point what I'd like to do is stop and do our first poll, and we're going to get your feedback on what tool you're using to predict fluid forces. And it looks like most of us are evenly split between CFX and Fluent, although we do have one outlier who's using another tool, so hopefully we can convince you to use CFX or an ANSYS Fluent. Okay, so let's move on to setting up our model. If I bring up CFX pre here, we'll take a look at the mesh that I brought in and the problem that we're going to be dealing with. The example that we're going to use today is we have this car, the sedan, that's traveling down the road at 30 miles an hour. And it's traveling straight down the road, so fortunately we can take advantage of symmetry here. And let's go through our setup for this problem. We just have the external flow, so let's go ahead and set up our domain. And as we go through, what we're going to want to take into account are the different options in our domain setup. So the first question that we come across is, what material to use? In this case, as I said, the car is traveling at 30 miles per hour, and the result of that is that the Mach number is less than 0.1. So we can safely say that we have incompressible flow here, and we're going to use the air at ambient 25C properties, which is a constant density. Now in the Fluid Models tab, since we're having incompressible flow, we can turn the energy equation off. We don't need the energy equation to be solved here. And then we're going to want to specify which turbulence model and wall function approach we're going to use. Now in this flow, we expect some level of flow separation. So we're going to use the K omega model, which tends to deal with that a little more accurately, along with the automatic wall function approach. Now if we take a look at the model setup that we have here, we have the inlet on one side. On the right-hand side here, towards the front of the car, we have our symmetry plane. We have the road on the bottom, and we have the other three surfaces acting as openings. So if we come back into CFX Pre and start setting up our boundaries, let's insert the inlet first. And since I created a name selection in meshing that was named inlet, it's automatically going to be scoped to the appropriate boundary. So I want to set the flow details to be a normal speed of 30 miles per hour and a medium turbulence intensity for the inlet should be appropriate here. So you can see our inlet is set up. The next thing on our list is to set up the symmetry plane. So again, I can come here, insert a boundary, set up the symmetry plane, automatically get scoped to the name selection that I had set up in meshing, and we're going to set that as a symmetry boundary. So if I move now onto the road, again, I have a location set up as road as a name selection, and I'm going to just set that to a wall. And no details here to set, just a no-slip wall for the road. Now, in the areas where the flow can, in the ambient areas where we have the openings, instead of setting those to be outlets, I'm going to let the flow along those sides act kind of as the ambient. So this is going to be the ambient sides, and that's going to be all three of those. And I want those to be openings. This way the flow can go in or out without placing a wall as an outlet opening would do. I'm going to set the opening pressure and direction to be 0 Pascal, and set the and normal to the boundary should be appropriate for the flow condition for now. Now once I have my my model set up, the next step in my after my boundary conditions is to set up my solver control. So if I come down into the solver section and set up the solver control, I'm going to increase the maximum number of iterations and make sure that my solution can run for a sufficient amount of time. And I'm going to set the automatic timescale factor to a value of 10. Typically, the timescale factor of 1 will produce a conservative estimate for the timescale used. So in this case, I'm going to bump that up a little bit, and I can always come back and reduce that or increase it further if I need to. I'm going to leave the convergence criteria as is, but I may find after my initial iteration that I want to tighten that up for a more accurate result. Now, when I'm judging my convergence, what I want to do in addition to using the residual target is to use some monitor points. So I want to make sure that the quantities of interest, for instance, the drag force, is fully converged when I stop the solution or when the solution stops. So in order to do that, what I'm going to do is set up in the output control some monitor objects. And these are very important to help you judge convergence. And you can set them up in a couple of different ways. So if I add a monitor point or expression, monitor point 1 here, I can either select a output variable at a specific coordinate, but sometimes what's more useful is to use an expression. So using CEL, or the CFX expression language, I can use the force acting on the car body as a monitor. So I will judge my convergence based on when that force value becomes constant or is no longer changing. So the expression that I'm going to use here is I'm going to use the force operator, and I'm going to use that in the X direction, so that's going to give me the drag force. And I'm going to select the boundary to be the car boundary. So that's going to be in my physics locators, the default domain, default boundary. And you can see that's this surface here. And so as I'm running, as the solution is progressing, what the solver is going to report to me is what the force value is on that on this surface. So as it's running, I can tell if that's physical. Maybe I can tell if I had some sort of setup mistake. And I can also judge, as the solution progresses, whether or not the solution is fully converged in addition to where the residuals are at. So if I accept this value, you can see the output gets added here into my output control, and I'll be able to monitor that during solution. Okay, so the next step in my procedure here is to define the solver run details. So if I bring over the Workbench project page here, in my setup, in my solution, I can right-click and edit. And then I'll bring up the CFX Solver Manager. And what I'm going to be able to do in the Solver Manager is define the details of the run. Bring that over into the correct screen. And in addition to whether I want to specify any initial values, I can say whether I want to run in parallel. So obviously, in this case, I want to run in parallel to take advantage of the HPC and run on multiple cores. And I can set that up in this solver definition. So as many, up to as many HPC licenses as I have, I can specify that number of processors to add to operate on the solution. So if I take a look at the solution details from the run that I already performed, I have a solution that converges in just about 150 iterations. I have my user points starting to level out. Probably need to let this run out a little longer in order to have a more converged solution, but should be sufficient for demonstration purposes. And my domain imbalances are sufficiently low so that I know, again, another judge of my convergence. Okay, at this point, let's stop for our second poll, where we're going to ask you for your input on using monitor points for judging convergence. So it looks like a fair amount of you are using monitor points, and certainly something that I suggest always doing. For those of you that aren't, certainly something that you should consider doing in the future in order to help you judge your convergence. Okay, so once we have our converged solution, well, the next thing we're going to want to do is take a look at it and open it up into CFD Post and visualize our flow field and do some quantitative results extraction. So if I bring my solution over into CFX Post, you see I come in with the wireframe view. And one of the first things I like to do for a solution like this, where I've used symmetry, is set up my transformation so that I can see the full geometry. So if I highlight edit the details of the default transform, instead of using the instancing information from the domain, I can apply a reflection about the symmetry plane, or the XY plane here, so that everything gets displayed on the full model. And it's just a little nicer for visualization purposes. It doesn't have any impact on the solution. It's just a graphics feature that we're going to use. So if I take a look, I have the road down here. And one of the first things I like to take a look at are some streamlines. So if I want to visualize the flow, I want to see what that looks like, what the flow pattern looks like. So I can go ahead and set up some streamlines here where they're going to originate in front of the car and allow me to visualize the flow that's going around the car. Now, one of the useful things is to have the car be highlighted. So what I've done is created a surface group. If I go to the location and insert a surface group and select all the surfaces or name selections that I had from the in meshing that represent the car body. This way I can turn on the graphics of the car so we can see the car body and give us some reference for how the streamlines are behaving. So if I use this surface group I had set up previously, I can see that as the flow comes in front of the car, I have the flow accelerating over the top of the sedan, and I have some a wake region behind the car where I have some slow speed flow and separation. So if I want to look at that in a little more detail, I can also look at velocity vectors. So if I take a look at the velocity vectors, a useful plane to use will be just the symmetry plane. And you see that by the default view, since my mesh is fine and the velocity vectors are pretty large, this becomes a little obscured. So what I can do is set the symbol size to be reduced to about 0.1, and this gives me a little more meaningful plot here. And what you can see is I have on the front end, I have the flow coming in and impinging on the front of the car. I have a well-resolved, boundary layer flow here, and I have some separation on the back end of the car. So a useful tool to visualize the flow details. And once I'm satisfied that this at least looks physical, the next thing I want to take a look at are the pressure contours. So if I take a look and insert a contour and use the surface group that I had set up to be the car body and use the local pressure, I can look and see that I have nice smooth contours. I have realistic contours. I have high pressure in the front, and I have smooth banded contours demonstrating the surface pressure variation across the vehicle when it's traveling at 30 miles per hour. So I can interrogate that. I can change the contour values so that they more clearly show what the flow looks like, and verify that things are behaving as I would expect them to be. Now from here, what I want to do is start to calculate some more quantitative results. So rather than just visualizing what the flow looks like and getting a qualitative feel for my analysis or for my device, I can use the calculators to get a more quantitative insight into the flow. So by using the function calculator, I can select from any of these functions that are provided by CFD posts. So a lot of quantitative functionality here. I can take the average of pressure or of any other solution quantity anywhere in the model. But what I'm really interested in here is what the force will be. So if I use the force, and I'm going to say, for instance, on the front wheel in the x direction, I can then calculate what that force would be. And you can see it's a pretty low value. We're not traveling that fast. And the wheel in this case is behind the is kind of inset into the sedan body. So I'd expect the forces to be rather low there. So using the function calculator, I can certainly extract quite a bit of useful information. Again, I can average, I can calculate average pressures, average velocities, things like that. But you may want to calculate more complicated expressions than simply just the force. So in the setup, what we discussed was that we would be interested in the coefficient of drag. So by using the expressions tab, I can insert a more complicated expression in order to calculate more complex variables. So if I want to calculate the coefficient of drag, I can create an expression that will predict, according to that formula, exactly what the coefficient of drag is. So if we recall back to the fourth slide what our formula for CD is, I can come into CFD Post and create a formula for the drag coefficient that's going to calculate that exactly for us. So you can see here this uses this expression here uses a couple of derived expressions, but if we went ahead and created a new expression, I would create using the CFX or CEL functions. I can recreate that drag coefficient expression. So if I want to use just the body for my drag coefficient calculation, first I want to use the force calculator, and then I want to do the force function, and then I want to divide that by 1/2 times the density, which I've set up as another expression called air rho, times the speed squared, which again is another expression that I had set up as 30 miles an hour. That's my free stream velocity. And finally times the cross-sectional area. So to go ahead and calculate that, you can see my coefficient of drag is roughly 0.314, which is typical of an automobile of this size and shape, and certainly points to the fact that our solution here is physical and in line with what our expectations are. Okay, so that's all that I have to show you today. In summary, fluid forces often play an important engineering role in engineering applications, and ANSYS CFD allows us streamlined and integrated tools for accurately predicting those forces. And using ANSYS CFD Post, we have powerful tools for flow field visualization and quantitative results extraction. So really a lot of powerful tools at your fingertips here, and hopefully you folks can take advantage of those and use them on your devices.